Okay, so we are finally starting chapter 2 on topological spaces and continuous functions. Now whatever we are going to discuss today will be done based on the assumption that you already know about metric spaces and continuity of functions between metric spaces. That's because that's how we motivate the definition of a topological space and continuity of functions between topological spaces. You can see that in the title itself, topological spaces and continuous functions. So, if someone asks what is topology, a one-line elementary answer would be like this. Topology is the study of those structures or those spaces where you can discuss continuity in the most general way possible. And that is why we need the notion of metric spaces. Well, actually, if you don't know about metric spaces and continuity of functions between metric spaces, or say you don't actually know about continuity, which is very unlikely, but still I am saying say that's the case, then also you will understand the definition of topological spaces, and then whatever comes after that, those things also you will understand. In what sense will you understand them? Like some games that kids make. Say some kids gather together and suddenly someone comes up with a bright idea that let's play some game today, and then they quickly make up some rules that if I run there and collect this many sticks, and whoever is going to come first to this spot, he will be king, she will be queen. It will feel like that. If the definition is not motivated from something else, it will feel like that. You will understand it, but it will seem artificial. That is why we are going to assume that we know about metric spaces, and that's how we are going to go with the study of topological spaces. So I am also going to assume that you actually know about how this motivation works. Let us go through that very briefly. It's all about continuity, in fact. Where do we come across this notion of continuity for the first time? In calculus. In calculus, we are told that functions of this type, which are very simple functions, the rule for this function may be complicated. It may be a trigonometric function, or it may be logarithmic function. I am not talking about that. I am talking about the structure of the function. It's the function whose inputs are real numbers and outputs are also real numbers. That type of simple functions. The reason for simplicity of these functions is that each one of them comes with a graph. And when you have something like that, it becomes very easy to understand some notions associated with these functions, like continuity, intuitively. Such a function, roughly speaking, is continuous if the graph is in one piece, it is not broken anywhere. That's why it is continuous. But then of course, when you go for defining this continuity, those nasty epsilon and delta inevitably rear their heads. That is because you want some way of estimating what is going on with the outputs of this function when the input is getting very close to some value. So limits come, and those you already know these things. So then you realize that when discussing this closeness of one variable to some value, you are actually using distance between 2 points. Your notion of distance from ordinary geometry. But then you realize that, okay, so if this is the case, then why don't I generalize the notion of distance itself to make the idea of a metric, say a distance measuring device using which I can measure distances between points of any set, not necessarily real numbers, any set of objects in some sense. That's how you get the idea of a metric space. And then when you apply this epsilon delta definition of continuity to functions between metric spaces, so there also you have a notion of continuity. Although for such functions, unfortunately there is no graph. You don't exactly have the intuitive idea of continuity that you have here, there, but that's not a very big problem. And then what you do, you then study the many things that come with metric spaces and continuous functions. You learn many things, how continuity interact with compactness, all those things, okay. But very quickly, after defining continuity of functions between metric spaces, you also learned the fact that continuity can actually be reformulated entirely in terms of open sets. You get the idea of open sets in a metric space. Roughly speaking, these are sets without boundary. These are sets which do not have, they may have boundary points, but the boundary points are not in the set, okay. So it's like a plot of land without any fencing, something like that. So you can now define continuity entirely in terms of open sets. So you do not have to talk about metric or distance. You know that that idea, that notion of metric is there in the background, but you have been able to reformulate continuity entirely in terms of open sets, which feels nice, okay. So then you get the idea of a further generalization. You think that if you use these open sets themselves and create a structure called a topological space in which there is no, maybe I should not say no, but there is no need for formulating any notion of distance between 2 points of a topological space, but everything that we are going to do will be done in terms of open sets. Sets of points or subsets of that set which satisfy some properties. What properties? Those properties you take from the properties that open sets have in metric spaces. You already know those properties. If you take any number of open sets in a metric space and take their union, then the union is also open. If you take finitely many open sets and take their intersection, then the intersection is open. And besides these two, we also have the fact that the entire space and the empty set are also open. These are properties of open sets in a metric space. But what you do when you want to generalize that to topological spaces is that you take these properties as your starting point and then define topology. I am not going too deep into this, okay, right now itself. At one point you may also think like this. In fact, I did. Okay, so the calculus definition of continuity was generalized to metric space definition of continuity and then to topological definition of continuity. Are these generalizations just generalizations for the sake of generalizations, or is there something deeper than this? At first it may seem that these are merely just generalization because we can, but that's not true. And today we are going to see how that is not true. Let's first see what I have written here. We are not going to consider arbitrary metric spaces. We are actually going to consider only that metric space that we consider in calculus. Consider the metric space of real numbers with the usual metric D that that allows you to calculate the distance between two real numbers and which has the absolute value function. The distance between the real numbers x and y is the absolute value of x minus y, that thing. Now, using this metric, you can define another such function like this, and I have called it d1. You can call it anything. What this d1 does is that the d1 value of x comma y, this ordered pair of real numbers, of course, is this. The d value of x comma y, which actually is just mod x minus y, divided by 1 plus d value of x comma y. It can be proved that d1 is also a metric on R, just like d. It also satisfies the properties of a metric, the definition, those conditions of a metric. And that makes R comma d1 also a metric space. D and d1 are not exactly the same, of course. You can see that here. Whatever distance d will measure between, say, the real numbers 3 and 4, and that distance would be 1. d1 will measure a different distance, the value will be different. But now comes the nice fact. It turns out that a function f from R to R is continuous with respect to d1 if and only if it's continuous with respect to d. This means that as far as continuity is concerned, it does not really matter whether you are using d or d1. The exact distance measuring device or the scales that you are using, the rulers that you are using for measuring distance, or the methods you are using for measuring distance between two real numbers, actually continuity is not fundamentally dependent on these things, but something else in the background is determining continuity, and that thing is topology. Let's see how. This is the reason for that. If G1 and G2 are collections of open sets in the metric space R, D and R, D1 respectively, then it turns out that G1 is equal to G2. And why does this tell us that this will happen? Well, because you already have a reformulation of continuity of functions between metric spaces entirely in terms of open sets. So if these two metrics on R are providing you with exactly the same open sets, obviously continuity ultimately fundamentally is depending on the open sets themselves, not the way of measuring distance. And that makes the definition of a topological space a significant one. It's not merely a generalization, because it is there in the background. This is actually what determines continuity, not the metric. So now let's see the real definition, and then of course the other things will come. So this is the definition of a topology. Topological space, of course, comes only after you have defined a topology. A topology on a set X is a collection tau of subsets of X. What does that mean? It means that you already have a set X and you also have another set X. The collection is, after all, it's a set here. And the elements in tau are subsets of X. So in that sense, tau itself is a subset of the power set of X. The power set of X has all subsets of X. Tau may or may not be equal to the power set, but in general it's a subcollection of the power set. And the elements in tau have some properties. Okay, so only such taus are going to be called topology, a topology on X. And these are the properties. The first property is very easy. The empty set and X itself are in tau. They are elements in tau. In tau, you have to understand one thing clearly, that the status of the set X and tau are slightly different. It makes sense for X to be an element of tau, but X is not a subset of tau. Although these two are sets, the objects that you have in tau as elements are subsets of X. So like these two are subsets of X, they will belong to tau as elements. So that is the first property that tau has. The second property, the union of the elements of any subcollection of tau is in tau. Simply put, this just tells us that if you take any elements from tau, and these elements will be subsets of X, and you take their union, you may actually choose infinitely many elements of tau if tau has infinitely many elements, does not matter. There may be uncountably many elements also, and you take their union, and that union of course is again going to be a subset of X, because originally the sets in that union were subsets of X, and that union is again in tau. The sets that you chose are from tau and their union is also in tau. So tau has this property also. And the third one, the intersection of the elements of any non-empty finite subcollection of tau is in tau. If you take finitely many, this time finitely many, okay, elements from tau which are subsets of X, and you intersect them, that intersection will again be an element in tau. You do not exactly, you won't see this non-empty, this term in the book, because it's understood that when we talk about intersection, we always consider a non-empty collection of sets. You go back to the preliminaries and see what goes wrong if you take the intersection of the empty collection. But anyway, so if such a subcollection of the power set of X satisfies these properties, then this thing will be called a topology on the set X. That's the thing. Now if I quickly summarize this thing, then it looks like this. You have a set X and you have a collection of subsets of X with three properties. The first property tells us that the empty set and X are elements in tau. The second property tells us that if you take just about any elements from tau and you take their union, that union is also an element of tau. And the third property tells us that if you pick finitely many elements from tau and take their intersection, then that is also an element in tau. Then tau will be called a topology on X. Now of course there are other things after this. And a set X with a topology tau on it is called a topological space, or more precisely we call this ordered pair a topological space, where X is a set and tau is a topology on X. So you can think of it like the ordered pair that we have in metric spaces, where you have a set and a metric. This time a topology takes the place of a metric. Next, if X comma tau is a topological space and U is a subset of X, then we will say that U is open in X if U is an element of tau. So the definition of open sets in a topological space is more simple than the definition of open sets in a metric space. They come from a metric, in this case also they come from a topology, but here it is more simple in the sense that the sets which are elements in tau are just called open sets. Okay, that's how we name the sets in tau. You may have other subsets of X also which are not elements in tau. Those are not called open sets. The elements of tau are precisely the open sets. And in this new terminology, now that the elements of tau have got this general name open sets, we can restate the conditions in the definition of a topology like this. The empty set and X are open if X is the set on which all these things are going on. The empty set and X are open, that is the first condition in the definition of a topology. The union of any arbitrary number of open sets is open, and the intersection of finitely many open sets is open. So that's all we have about this definition. Now next, of course, naturally come the examples. That however we will discuss in the next video. So that will be all for tonight. See you tomorrow with something new. Until then, this is me, Lucifer from A Mathematical Group. Have a nice day.